Okay. I hate when I put gas in my car and my hands smell like gasoline. Such a terrible smell. Okay, chapter 31. Moving on to radioactivity and nuclear physics. By the way, we haven't discussed this much, but I actually did this on my own. I got permission and funding to go to UNL, which happens to be like in a week and a half, to go to the open house for engineering. Do you guys want to go to that? It would be next Thursday and Friday. We would leave Thursday morning, and we would go, travel up to Omaha and go to the Air and Space Museum. Spend the afternoon in the Air and Space Museum because they're doing the science, they're doing this Nebraska science something there. So we'll go there first. And then I'll turn you guys loose in downtown Lincoln to do whatever you want that night. And then in the morning, we would get up and go tour campus. And then at noon, we go to the open house and engineering. It's actually going to be at the stadium this year instead of in the engineering department. So it's the tour of the engineering department probably in the morning. Maybe some of the other places on campus. And then go to the stadium, football stadium, and see all the projects of the seniors and meet all the professors. And then we would come home. And I got funding for the travel for this hotel stay and for meals. So, for 7 people total.
So we leave Thursday morning and
We'll be gone overnight, 2 full days. I don't know if that's enough time for you to get work off or anything else like this, but it's a great opportunity to see what's going on in UNL, to meet professors, kind of know what's going to be expected of you when you get up there, meet lots of students. Also, lots of engineering companies show up for this thing to recruit, and so you can go around and see what kind of companies. They usually have a lot of information, a lot of handouts. They usually give away a lot of cool stuff, actually. But make a lot of contacts there for future, for internships. One of my students, while he was there, met up with the OPPD people, got an internship, paid his way through college, and then gave him a job and got out. He works at the nuclear power plant, making a lot of money. But it's a good opportunity, so I highly recommend you make time and effort to come with us. I have spots for 6 or 7 people in the van. I don't know how many it holds. I think it holds 7 people, but it may just be 6. So I have spots in the van, and need to know probably at the latest week from today. Okay?
It's not this.
It's not this Thursday, it's next Thursday. I'll be inviting people from physics and then people from the STEM club to go. Essentially, it's going to be first come, first serve for the van. So, and it's, we'll have, breakfast is provided at the hotel. I'll be asking you to provide your own breakfast. But essentially how it works is with this, how it's worked in the past, and I assume it'll work this way this time, is I requested 2 dinners and a lunch, or 2 dinners and 2 lunches, or something like this, for each person that goes. And so for dinner you get like $24. For lunch you get like 14 or something. And so you end up getting 13, I think. But you end up getting this certain amount of money, 50 or 60 bucks, and I just give it to you in cash. And then you just spend how you want to. It's up to you. While you're there, you can spend it on all your meals or pocket it and bring your sack lunches if you want. But you have to sign. You have to just sign that you were there on the trip and you used the money. You took the money set aside for you. And in the past, they haven't collected receipts or anything, so it should be fine. So you're responsible for your own breakfast on Thursday morning, unless we'll probably make a stop for breakfast and make a stop for lunch on the way. We'll probably be there by lunch, I would imagine, because we'll probably want to leave around 5 or 6 in the morning. Try to leave as early as possible because we want to be there. I think that the city of North Platte is going to have a booth at this science thing, and I told them that we could man the booth for a couple of hours because that gets us in free to the museum. Have you guys ever been to the museum? That's good. Great. The Air and Space Museum. It's actually called the Strategic Air Command Museum, but it's lots of airplanes and rockets and cool stuff. They have an SR-71 in the lobby, which is really kind of cool. Fastest plane ever built.
And where is that?
It's just outside Omaha, just south of Omaha. Used to be a bomber base.
I don't remember, but I remember when I was young, it was like an air space museum.
The big rockets on the outside?
I honestly can't remember. I remember the SR-71 was hanging up on
Yep.
right when you walk. I'm
Yep.
not sure that
That's it. That's the one.
probably is.
Yeah.
Pretty interesting.
It's a really cool museum, and it's grown over the years. And it's a big place. They have a B-52, I think.
Yeah, they have a warehouse full of
Yeah.
airplanes.
The B-52 is a huge plane, and they have a B-52 inside the main hangar there. Just incredible museum. So. But yeah, it's a really cool one. And I've been there once. I went to a dinner there a couple of years ago. I was really impressed. So anyway, I wanted to go there this year, and if we volunteered to sit at this booth for a couple hours, we get to get in for free. So we have 7 people there. We can have 2 people at the booth, and everybody else can be wandering around, and we switch, and we can do all the activities they've got. They've got flight simulators and other cool stuff. And just lots of cool stuff. So what's the booth for? It's to promote the eclipse. So one of the things I've been having, I have a work study student works for me. I've been having him put together these envelopes of materials to hand out to people. Just information about the eclipse. These ones we're handing out in our area, but we'll hand out similar materials at that booth. We'll have probably goggles and information sheets and flyers to talk about what a great place it is to see the eclipse out here in western Nebraska. Which it's way better than Omaha. You won't be able to see it all from Omaha, really. But if you stay out in eastern Nebraska too, there's downsides to that because there will be a lot of people out there seeing it, going to see it in like Grand Island or Lincoln. The viewing is not really as good because of the obstructions too. Come out to western Nebraska, there's nothing to get in the way of seeing it. So should be a lot of fun. Anyway, that's kind of our plan. Probably that night, that Thursday night, we'll probably go into our hotel. We'll probably stay at the Hyatt Regency. Have you been out to this thing before with me?
I went 1 year.
Yeah. The nuclear power plant? Okay, so the same hotel we stayed in that time, which is the Hyatt Regency, that's the one we'll stay in. It's a really nice hotel. And but it's cheap for us because we get the government rate. And it's right down there in the Haymarket district, so there's just tons of cool stuff to go and do and see. There's lots of like clubs and restaurants and shopping, and it's a cool place to hang out. So we'll just go there that evening, that afternoon, right? And I'll just turn you loose down there. We'll check in, and you guys can go off and do whatever you want to do. Enjoy the city life a little bit, and then the next morning we'll get up and go down. We'll get up and go to campus. See if we can. Well, I will actually try to arrange a tour. They're going to do some tours in the afternoons, but I want to arrange some morning tours for us. Because once we go to the thing up at the stadium, I just want to stay there. But anyway, I wanted to arrange some tours to see the entire campus and see the engineering department. So anyway, that's what's coming up for that. And we'll hopefully get a good participation in that. I got 3 hotel rooms. I'm going to get 3 hotel rooms. And should do that today. Anyway, so radioactivity, nuclear physics is where we're at today. Yes, synchrotron, electromagnetic radiation. What's that? Didn't we already do chapter 3? Oh no, we did introduction to quantum physics. We didn't do atomic physics, did we? We need to do atomic physics. Never mind. Let's do atomic physics instead of radioactivity. All right, atomic physics instead. That's okay, because that's my specialty, supposedly. That's what my master's degree is in. Oh, anyway. All this stuff is all related to quantum physics and particle physics and other things like this. And atomic physics is just a particular realm of it that specifically deals with atoms. And atoms, of course, as I've mentioned before, were first hypothesized by a Greek guy named Democritus over, about almost 2,000 years ago or so. I don't know how long ago it was, a long time ago. But his hypothesis went something like this. You take a rock and you break it, you get 2 smaller rocks. And you keep breaking, you get smaller and smaller rocks, and eventually you get dust. And if you keep breaking things as small as you can break them, eventually you get to something you can't break. And he didn't know what that was and how long it would take to get to that point, but he said, I think that all matter is made of something that is unbreakable at some level, some small level. And he said, he called it the atom, which in Greek means unbreakable or indivisible. And so that is the name that we gave to this idea of the atom. But it wasn't until much later that we actually discovered the presence of atom-like things. And this is one of the experiments. This is an experiment done by a guy named Brown, where, I can't remember his first name. But anyway, this guy named Brown did this experiment where he had these pollen particles under a microscope in fluid, I think oil or water or something like this. But he noticed that the pollen particles, even though there was nothing in the liquid moving that he could see, the pollen particles every once in a while, well, not every once in a while, but constantly, went through this jittery random motion that if you measured their average position would be in the middle of this motion somewhere. But this motion would take them in every direction at different speeds and all kinds of things. It was eventually called Brownian motion, this erratic random motion. And it was Einstein that described this or explained how this random motion could come about. And his explanation was that the universe is made of these tiny little particles that we can't see, that we can barely detect, hardly detect. But this is one of the detections of these particles, and that these particles are moving with enough energy to move very small things like pieces of pollen or dust that we can see. And that this random motion is due to these collisions with these tiny particles we can't see, and we call them atoms, but most likely at that point we were talking about molecules of water, for example, in the water. But anyway, this is pretty close to atoms. A molecule is made of several atoms, moving around, several atoms connected together, moving around in these motions. And So it's pretty good. It's a pretty good experiment, and he was Einstein was one of the first people to kind of make this connection between the macrocosmic world we live in. Oh, here's his name, Robert Brown. He was Scottish. Scottish. Anyway, later on, this guy Jean-Baptiste Perrin, he actually was able to carefully measure this Brownian motion of particles and confirm that Einstein was correct in this, making some calculations and other things. And in very later days, very recently, we have actually been able to detect single atoms. And in this particular case, we're detecting single atoms of gold on a graphite substrate. So this is gold on top of a pencil, right? And the way that we detect them is through a thing called a scanning tunneling electron microscope, or we can also use a atomic force microscope. The scanning tunneling electron microscope we've already talked about, where you have these electrons that have that wave-like nature of electrons, and as they go through a material, the wave is interrupted, or the wave is affected by particles around it, and we can measure that effect by seeing how the electrons diffract through a material, just like light diffracts through a crystal. And it makes patterns, and those patterns can show us, where the atoms were as the electrons traveled through or tunneled through this material. With a atomic force microscope, they use nanotechnology to make a very, very tiny needle, like the needle of a record player. And this very, very tiny needle is scanned across a surface, and since it's a very tiny needle, it is affected by individual atoms. Like the tip of this needle is only a few atoms wide, like maybe 10 or 20 atoms wide. So it's extremely sharp. But that sharpness of it means that it's going to be affected by or pushed by other atoms. It will be able to detect other atoms one at a time. And as it gets pushed by them, there's a little mirror on the back of the arm where the needle is, and that mirror has a laser bouncing off of it, and that laser is moving on a long lever arm as this needle bounces very, very slightly. So they've been able to use atomic force microscopes to also measure. We say to see these atoms, but we're not really seeing them. We're just detecting them. Here's an atomic force image of proteins. So these proteins are made of rings of carbon atoms. So you're seeing carbon atoms there. Here are some, don't know what those are. They have image, that's tin. So those are, I don't know what all these things are, but here's one that actually shows us we're at the 1.9 or 280 nanometer level to 0 nanometers. So we've got the bright spots are at higher. I mean, they're able to measure nanometers, which is only a couple hundred, well, maybe a couple thousand atoms. Here, for example, this is atomic resolution of graphene. So we're looking at actual bonds between atoms. Each one of these corners would be an atom at the graphene level. I mean, at the atomic level for graphene. So you're actually seeing the atomic crystalline structure here of something. So they're able to confirm a lot of the things that we've made theories about how atoms connect together to make molecules and so on and so forth. Here's a picture of how that atomic force microscope works with its laser and the detector and the little needle down here that bounces up and down. And you can actually see an image of the needle. You can make a microscope image. Here's a microscope image of a scanning atomic force microscope needle. This is actually a better one, where they have this cone kind of pyramid-shaped needle, and then on the end of it they grow usually a carbon nanotube that is less than 200 nanometers across. So not that big at all. It's super tiny. Here's another example of one here. So another image of one. This is made by a scanning electron microscope, a surface scanning electron microscope. So anyway, lots of new technologies for us to learn about atoms that in a very in the most direct way we've ever learned. It's still not direct. It's still an indirect detection method, but it's much more direct than we've ever been able to do before. So very interesting stuff as we learn about atoms. And okay, so parts of the atom. How did we discover the parts of the atom? We knew about the basic constituent parts of the atom for a long time. We've known for a long time, for example, that there are electrons in atoms. And one of the reasons we know that is because in cathode tubes light up. These are like the neon tubes you see in light displays and everything else. Cathode tubes they light up because of accelerated electrons. You have an anode at one and a cathode at the other, and you accelerate electrons from one end to the other, and this accelerated beam of electrons goes through a gas, and as those accelerated electrons go through the gas, they excite the gas glows. That's how you make it. So it's not a new thing to understand these charges, and we've been able to detect these charges ever since we started doing electricity and everything else, and all the charge experiments we've done all semester long. This is, 1800s stuff. We knew about this in the 1800s, maybe even late 1700s. We started to learn about these things as people like Benjamin Franklin flew his kite, to figure out the electron. So we knew that matter was made of charged particles, but we didn't know how it went together. We knew that the one charge that we now call the electron because of Benjamin Franklin could be moved from one material to another. So if you rub the cat fur on the amber, you get charge that moves from one to the other. We knew that, but we didn't know which charge moved first and foremost. We didn't know which one moved for a little while. It took some time to figure out. But then after that, we didn't understand what was the nature of the other charge. Once we figured out it was the electron that moved back and forth, and that was the negative charge because of Benjamin Franklin's decision, then we didn't know what the positive charge was all about. We just knew that it didn't move. We knew that it stayed put in the material, and the electron moved back and forth to make things either positively or negatively charged. And so a lot of experiments had to be done, and a lot of theories had to be made. And one of the first theories was made by this guy here, J.J. Thomson, English physicist, and he did a lot of experiments with electrons and other things, and learned about how electrons could be detected with electric fields, and also deflected with magnetic fields and other things. All things that we've learned before, and all equations that we've dealt with before. None of this is really new, but two things that were discovered. One thing was discovered through doing experiments of deflecting with electric fields and with magnetic fields, is the charge to mass ratio of the electron. So we learned that the charge to mass ratio of the electron is negative 1.6 times 10 to the 11 coulombs per kilogram. And then the charge to mass ratio of the proton was discovered because we discovered that there was this other charge, and we discovered that the proton was much bigger than the electron. And then eventually Coulomb came along and was able to actually measure the charge of the electron. And that gave rise to the idea of the quantized charge and other things like this. However, and that was Millikan's experiment. That's the oil droplet. Did we do the oil droplet experiment this year? I don't think we did. But anyway, so lots of experiments being done to figure out the mass of the electron, the charge of the electron, the mass of the proton, all this stuff. However, we didn't know what atoms were. We knew that there were positive charges and negative charges out there. We didn't really know what atoms were. So this guy came along and said, I'm going to make this theory. And this is actually Thomson that made this theory. Thomson came along, and being English, he said, I think that everything is like plum pudding, because plum pudding is so fundamental and important to the English. If you're not aware of what plum pudding is, it's like a cake that's very dense, it's very moist. It usually is filled with dates and nuts and raisins and things like this. And the plum is used to sweeten the pudding, because sugar was not readily available in Europe. Sugar was something that came from the New World, came from America. So they used fruits to sweeten things, and plums were a very available fruit in Europe. So this pudding, which is really kind of a wet cake, was very thick and very dense and very moist, very dark from the plum, and it had these raisins in it, raisins and nuts and things in it. So he said it's like a plum pudding. Everything in the world is like a plum pudding. And atoms are going to be like a little plum pudding with these raisins or dates or nuts in them that are going to be the positive charges. Those are going to be the electrons. But the rest of it is just going to be this mix, this amalgam, this cake of stuff. And when you have a lot of those put together, you can make a house, or you can make a brick, or you can make a rock, or whatever else. That's what matter is made of. Well, people tried to start to test to see if this theory was true. And the most successful test was the test done by Ernst Rutherford. Ernst Rutherford earned the first Nobel Prize in chemistry for this experiment. Ernst Rutherford earned his Nobel Prize in chemistry for this because he pissed off the committee, the Nobel Prize committee. Ernst Rutherford was disdainful of all sciences except for physics. And he stood in front of a bunch of scientists, including scientists on the Nobel Committee, and said, the only real science is physics, the rest is just stamp collecting. So they refused to give him the Nobel Prize in physics. They gave it to him in chemistry instead. But anyway, this was the experiment that he did. He had this source of alpha particles, which is essentially just a radioactive source like radium or plutonium, or uranium or something like this. And what is an alpha particle? Well, what they knew about alpha particles at the time is that they knew that they were massive particles. They were much bigger than electrons. And they had positive charge. They had twice as much charge as electrons, but they were way more massive, like 5,000 times more massive than electrons. Huge, huge, big particles. And these alpha particles would come out with a fair amount of energy. And there was a little hole in this box so that they would come out in a straight line. And then he put it inside this machine, and originally this machine only had a screen on this side. It didn't have a screen on this side originally. Originally it only had it on this side, and these particles would come through, and he put it through some gold foil. Now gold has a very specific, very unique property that you can hammer it out, hammer it out, hammer it out, and make it thinner and thinner and thinner and thinner and thinner and thinner until it is only a few hundred atoms thick. You can make gold foil so thin that you could take this ring, if it was pure gold, but it's not. If this was pure 24 karat gold, you could take this ring and hammer it out to the point that you could cover my entire body in gold with just this much gold. Okay? Doesn't take much because it can be hammered so thin. And when you see these buildings in Russia that have gold on the outside, or big statues that are covered in gold, that's how they did that. They would cover it in gold by making a very, 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 very thin sheet of gold and cover it with this extremely thin sheet of gold that would then shine like gold. If you hammered out gold as thin as it can hammer out into a sheet this big, it would barely be worth $1. I mean, it wouldn't be worth very much because it's not very much gold. It's so little gold that it becomes extremely delicate. It can be torn very easily, for example. But anyway, gold, it's called gold leaf also, but I've actually got some in some of my instruments here. But gold leaf is extremely unique in that way. The metal gold is extremely malleable. So they had this gold foil in here that they were hammering with these alpha particles, only a few hundred atoms thick. And what Rutherford said is that if you don't have very many atoms, just have this thin layer of gold atoms, then most of these alpha particles are just going to hammer their way through the pudding. They're going to go right through this plum pudding that is the atom of gold. But every once in a while, they're going to get close enough to an electron, one of those raisins in the pudding, that the electron is going to attract the alpha particle because opposite charges attract, and steer it off course a little bit. And that's exactly what they saw. They saw the gold particles going in. Most of them went straight through. Some of them got steered off course a little bit. Perfect. Then one of his students came along and set up a screen behind this. And that was brilliant. Because what they saw is that 1 in 1,000 of these alpha particles would actually bounce almost straight back. It's like they were going in to this plum pudding, and instead of encountering a raisin, they encountered a chunk of lead that was so massive compared to the particle that was going in that it just bounced it straight back out. And they're like, wait a second, this doesn't make any sense. That doesn't fit our theory. In our theory, we just have this soft stuff that's positively charged, that's like the pudding. And then the positive charge is just kind of spread out in there. And then, and anything, any big massive charge, like the alpha particle that goes through it, it's just going to hammer right through it. It's got so much energy and so much mass, it's just going to go through it like a bullet through butter. So having these particles come straight back out would be like shooting a machine gun at a birthday cake. And then all of a sudden having 1,000 of your bullets come straight back at you. It really surprised them. They're like, what's going on? The only theory that could explain this was that, first of all, this theory of the atom being this fluffy thing of stuff with just these little tiny particles that might steer things off a little bit must be wrong. The only theory is that somewhere in matter there are very small, they have to be about 1,000th of something that's very small but very dense. And it has to be about 1,000th the size of the atom. So it's very small compared to the atom, 1,000th the size. But it has to have so much mass that a very, very highly energetic, very fast-moving, massive particle that comes in doesn't affect this small thing at all and gets pushed right back out in the opposite direction. Okay? And that small thing has to be positively charged to repel it like that, too. So what they said is instead of this positively charged stuff being spread out in this big cake fluffy stuff, all that positive charge is actually concentrated into a tiny little part, a tiny little piece where all the mass of the atom must be, or most of it, the vast majority of it. So you have all this highly dense material all in one little spot, and it has all of the positive charge as well. What do we call that thing today in the atom? We call it the nucleus, right? The nucleus of the atom is where all the positive charge is in the atom, and it's where most of the mass is in the atom, right? So that when something massive comes into it, like an alpha particle, and hits that gold nucleus, which is way bigger than the alpha particle, the gold nucleus hardly even feels it, but the alpha particle gets kicked way back out, right? Also, those nuclei, the nucleuses, are the things that were actually deflecting the alpha particles, not the electrons. The electrons have almost no effect on the alpha particle. They're so tiny. They may have a lot of charge to them, but the nucleus of these particles has way more charge. So instead of going in, when you're going into a gold as an alpha particle, instead of feeling like you're shooting through like cake, it's actually kind of like going through a forest where there's one tree every, like if this room was the forest, there would be one tree in this room, and the one tree in this room would only be about this big around. It's like throwing a frisbee into a group of trees where there's one tree in a room this big, the tree is only this big around. Most frisbees go straight through, but if you get within, maybe 10 feet of that tree, it'll turn the frisbee a little bit. It'll turn it away from the tree. So most of your frisbees are going to either go straight through or get turned a little bit. Some of them are going to be really close to the tree, so they're going to get turned a lot. And every once in a while, about 1 in 1,000 shots, you're going to hit the tree dead on and it's going to come straight back. Actually, the tree would have to be much smaller than that. This room is 20, I think it's about 24 feet across. And so 24 feet is 24 times 12, 2,400, 2,500 inches. So, yeah, it'd have to be about this big. The tree would have to be about this big around for it to be true. So essentially the circle at the middle of that thing would be your tree, about half of that circle, I guess, would be your tree thickness. And any frisbee that came close to that would either get turned. If it hit it, it would get kicked straight back out or at an angle out. And so anyway, and that's actually, I developed a nuclear science class 10 years ago now for high school kids. High school kids would go to university. It's actually done. I did it with the Johns Hopkins University Center for Talented Youth, is what they call it. And Johns Hopkins University in Baltimore, very, very good university. They do these kind of like summer camps, 2-week-long camps where you go to a university near you. I was at the University of California in Santa Cruz. probably the ugliest buildings at a university you've ever seen. They just looked like army compounds, just blocks of concrete. Terrible, ugly buildings. But in the most beautiful place on earth, right in the middle of a redwood forest on the Santa Cruz Mountains overlooking the Monterey Bay of California. You know, you wake up in the morning and there's beautiful fog in the redwood forest. You go walking down through the redwood forest, and then all of a sudden the vista opens up to the Monterey Bay, and there's humpback whales or dolphins going across the bay or something. Just the most beautiful place with the most ugly university ever. But just a funny place. But anyway, there in the redwood forest, I got a bunch of frisbees and had my students throw their frisbees into the forest. And then we would take data from this. So anytime a frisbee landed near a tree, we would call that a deflection. And depending on how close it was to the tree, we gave, you know, if it was 5 inches from the tree or 6 inches from the tree, we would call that a deflection of 30 degrees. But if it was 12 inches from the tree, we'd call it a deflection of 20 degrees, and so on and so forth. But if it actually hit the tree, then we would call that a deflection straight back out. And we were actually able to do our own macrocosmic Rutherford experiment to determine how big atoms would be if the atoms were these trees, and so on and so forth. So it's kind of cool. But anyway, that is the Rutherford experiment. And from the Rutherford experiment, he came up with a new model for the atom. And the model is called the planetary model, or the Rutherford model, where you have positive charge at the middle that's very tiny, and electrons orbiting around the outside like planets in a solar system. And this model is great as long as you didn't think about the physics. As long as you only thought about, you know, planets and very basic science of the time, it was great. But the physics of this, physics absolutely prohibits this. And the reason for that is because things that are traveling in circles are accelerating, aren't they? And it was known, even at that time, that particles that have charge that accelerate give off light. Okay, it wasn't really well known, but they were learning that at the time. And if you give off light, you lose energy. That's something that they did not know at the time. They were still learning that when you give off light, you lose energy. But it wasn't very long afterwards that they discovered these things. So that if you're going around in a circle and you're a charge, like an electron, you're giving off light, you're losing energy. If you're losing energy, then your orbit has to decay. Your orbit has to get smaller. And if you continue to orbit, you continue to lose energy, you continue to get a smaller and smaller orbit. Eventually, the electrons would collapse into the nucleus. And then the atom would collapse. And then the entire universe would collapse, right? So obviously, this can't be the case. If this was the case, the entire universe would have collapsed a long time ago, and we wouldn't exist. So there's something different going on than just electrons orbiting around a nucleus. And it took a while to figure out a model, to create new models for this, and to accept them as well, because it was very difficult to accept that electrons exist around atoms but don't move around atoms, don't accelerate around them. It required a whole new way of thinking and a whole way new of accepting the nature around us. Since we can't actually see the electrons around the atom, we have to rely on indirect evidence, and then we have to create models and test those models. And once those models are tested and shown to be true, we have to accept them. We can't just say that can't be, because when they started doing this, they just started discovering things that they didn't believe. They started understanding things about atoms that they couldn't accept, that they had a hard time believing. Einstein didn't accept most of this stuff because he just wouldn't believe that this is the way it was. But this was the only explanation. And all of the models and all of the experiments were holding this up, were supporting it. So it starts to get really weird here from here on out. Even weirder than before, if you can imagine it. Gets even weirder than relativity. So along comes Niels Bohr. Niels Bohr, brilliant Danish physicist. He's looking at this atom and he's saying, no way, this can't happen because of the energy problem. And then he looks at some other things that people were doing, which include atomic spectra. At the time, they were using these cathode tubes where you accelerate the electrons, but they were using cathode tubes, they called them discharge tubes at the time, to look at specific gases. So what you do is you put a gas like mercury gas or water gas or oxygen gas or something like that inside of a tube, And then you excite the gas inside that tube either by pumping electrons through it, by heating it up, putting a voltage through it, something. You excite the atoms in there, and it makes light. And every gas makes a specific color of light. And we're going to see some of this here this week in our experiments this week. But as each gas was lit up and made a different color, they decided to split the light. Remember, splitting the light with optics, you put it through the prism at that high angle, that really sharp angle, and it splits the light into the rainbow. When they did that, this is what they got. Instead of getting a rainbow, they got specific frequencies, specific wavelengths, just these colors, just those colors. And it's different for every gas. So for example, this is the hydrogen, when you do hydrogen gas. This is the spectrum that you get, or the lines that you get. Way over here at 1875 nanometers, you get this deep infrared light. You can only detect using infrared methods. You can use infrared film, for example, and that's what they were using at the time. And then as you get closer into the infrared, you get some out here in the 1500 nanometer range, somewhere in there. You get these other ones, I don't know exactly what they are, but eventually you get into this range here where it's visible light. You get one at 656 nanometers, you get this one at whatever it is, you get eventually one here out of 365 nanometers. So everything from the red side of the spectrum to the blue side of the spectrum, you get these specific lines. But there's some interesting things about it. First of all, they're characteristic. Each gas is different. Each gas has different lines. They have different combinations, different spacings between them. But notice the spacings. The spacing between this one and this one and this one is huge. Then this one is smaller. Then this one and this one is smaller yet. And it actually follows a mathematical pattern. And this one also follows a mathematical pattern. And so does this. In fact, they all follow the same mathematical pattern. You have these big gaps at the beginning, and then they get smaller and smaller and smaller. And the math is the same for them all. And it's the same for all gases, in fact. All the pattern is the same, even though the numbers and the spacings aren't the same. The pattern is the same. And Niels Bohr started to look at this and said, well, what is the pattern? And he created an equation for this pattern, and this is the equation. 1 over the wavelength is proportional to a difference between the number of the line. So if you number these lines from, they number them from, they actually are numbered from 1 to infinity. In this case, it depends on the series, though. You can number it from. Well, anyway, you have these numbers, these ends, and if you take the difference between two of these ends, you can actually calculate 1 over the wavelength. And then there's this constant in here that ends up being in there they call the Rydberg constant. But this equation predicts where these lines will be if you know the first one or the second one. I mean, this is the model. This equation fits this pattern. And he said to himself, well, how does that correspond to the atom? What does that mean for the atom? And he said, what if the electrons only can exist at certain levels of energy and can only go between certain levels of energy, and between those certain levels of energy is where you get these different wavelengths of light. So if you go between the first level and the second level of energy that the electron can be in, then you get this particular wavelength over here. This particular line comes out of light. But if you go between the first one and the third one, you get a different wavelength of light. And that's another line on here. And that is the theory that he came up with. His theory was electrons don't orbit around. They exist in these energy levels around the atom, and they can jump from one to the other, but they don't exist in between. They don't stop in between. They don't travel in between. They just make this quantum jump, this quantum leap from one level to another. And the energy is expressed as you see it in the spectrum. Because these atoms that are being heated up or exposed to some high voltage, all of their energy levels are being exposed. All the electrons are jumping back and forth between all the energy levels all the time because they're so excited. And so you see all of them at once. So anyway, this is the Bohr equation, also sometimes called the Rydberg equation. But anyway, it's got this Rydberg constant in it, named for another scientist that was working on this stuff as well. And you can calculate the wavelength of any spectrum between any two energy levels in the atom. And the energy levels, you can think of them as orbits or distances away from the atom, whatever else, but they're not really that. They're just energy levels. And this is what, for this equation, we call this the principal energy level, the principal energy levels, or the principal quantum number n. So these energy levels are quantized. They come at specific levels, at specific numbers, and only those numbers. And the quantization comes down here in these n's. So let's look at an example of using this model or this equation. So, oh, this is not even, oh, it is using it. Okay. So here they're asking, what is the distance between the slits of a grating that produce a first order maximum for the second Balmer line at an angle of 15 degrees? So this is a bad question, I think, for this part of the book. But they're essentially asking us to combine something that we learned earlier when we learned about wave interference with something we're learning about right now. Wave interference, the angle of wave interference depends on the wavelength of the light. And so here, they're saying we're going from the first order to the second order Balmer line in, so first order, meaning that's n equals, we have to actually look at and see what the first order and second order is in the Balmer series. So we go up here to our thing here. The Balmer series actually starts at n equals 2, and it goes from n equals 2 to n equals 3 to n equals 4. So the first order is actually the n equals 3, n equals 2 being the 0th order. The second order is n equals 4. And they're asking us that when it goes from, produces the first order maximum. So the final is, it always goes down to nf equals 2. So the first line is going to be ni equals 3. And they want to know first order maximum, right? Let's see, what are they saying here? They're saying that they're going for the second order because they're doing n equals 4, not n equals 3. The first order should be n equals 3 to n equals 2. They're saying it for the second. Oh, no, because it's the second Balmer line. They want to know the first order maximum for the second Balmer line. Okay. So the second Balmer line is going to be, the first Balmer line goes from 3 to 2, because the Balmer series always ends at n equals 2. The Lyman always ends at n equals 1. This one always ends at n equals 2. I want to show you a different version of this. Here's a different version of this to kind of explain this. The hydrogen, all atoms are made of these different energy levels, which you could represent as orbits like this. And you could also represent it like this, where this is the first orbit. This would be this first one down in here, 1. And this one would be the second one, so 2, and so on and so forth. The bigger distance that you jump, the higher frequency of light you're going to have, or the shorter wavelength. So anything that jumps down to the first level, any electron that goes from a higher level down to the first level is going to have a pretty big jump. And those are going to be this series that has these really low wavelengths out here, the Lyman series. Anything that ends at n equals 1, or the first energy level. It jumps from any higher level down to that first energy level. It gets these really high energy wavelengths. And then the second level, which would be the second one right here, anything that jumps from above here down to that second level releases the light that ends up showing up in the Balmer series. So we're looking for anything that ends at n equals 2 from anything above n equals 2. The second order, or the second line in this one, is going to be jumping from the second line above n equals 2. So n equals 3 is the first one above n equals 2, n equals 4 is the second one above n equals 2, and that's why we use n equals 4 here. And this is why I think this is a bad problem, because they should give us a simpler one to start with. But anyway, the point is that we're going to go from n equals 4 to n equals 2. N equals 4 is our initial, so that's the second one here. N equals 2 is our final, that's the one where we end up. So we go 4 squared, 2 squared in these two spots, and then we do the math. We plug in a Rydberg constant, and we get 2.057 times 10 to the 6 per meter. So you have to invert that, and when you invert that, you get 486 times 10 to the minus 9, or 486 nanometers, which is in the Balmer series here. It's between 365 and 656. So that's in the Balmer series. 486 nanometers. I don't know exactly which one it is. It's the second one, so this is the first one. So this one must be the 486 one right here. So anyway, you've got your 486 nanometer line now in that Balmer series. Now we need to use that with our double slit interference from wave optics chapter. It's d times the sine of the angle theta. The angle theta they gave to us is 15 degrees equals m, which is the order of the maximum we're looking at it. They wanted to know the second order maximum, I believe. No, first order maximum, so we know m equals 1. And then the wavelength of 486 nanometers. You solve this for d to get the distance between the slits, and you get that right there. So that one was solving that one required several steps. Like I said, I wish they would have given us a better one, a simpler one. But in the end, what Bohr's model was all about was difference in energy levels between the energies that the electrons could have in hydrogen. His model really only works for hydrogen, and it's never really expanded to much more beyond that. Trying to model another atom besides hydrogen is extremely difficult because the simplicity of hydrogen, one proton at the center and one electron that jumps between these different spots, the simplicity is great. It makes it very easy to understand. But helium, you have 2 protons. That's not a big deal. They're pretty close together. It's just, twice as much charge down there. But then you also have an extra electron. So the extra electron in helium affects the first electron. They affect each other. They start to get in each other's way. They start to mess with each other's, voodoo. And so it really gets complicated, even just going to helium. And if you get to something like, calcium, you got 40 electrons, I think. Let's see what's calcium. Where's calcium? No, that's zircon. Calcium is, where's calcium? No, that's not calcium. There's calcium, 20. It's got 20 electrons. Calcium has 20 electrons. Each one of those electrons messes with the other electrons. They attract, they repel each other, they mess with each other's energy levels. It's extremely complicated. The one that has 40 is actually zirconium. Zirconium has 40 electrons. I mean, you can get crazy busy out there in the electron levels, the energy levels. And it's very difficult to model those. If you strip all of the electrons off of calcium except for one, then you can use this theory again. So this theory, even though it explains a lot, it only explains a little. So, we're woefully ignorant about a lot of things still about the atom. This is often the way energy levels are portrayed inside of an atom, because this shows you all of the differences in energy. If you consider that n equals 1 is the energy level closest to, quote unquote, the atom, closest to the nucleus, you can see that there's a huge jump between that first energy level and the next one. It's very difficult if an electron is at that low level, that what we call the ground state of an atom. It's very difficult for it to jump up and jump out of the atom because it's so tightly bound. It requires that huge jump between n equals 1 and n equals 2. Again, n equals 1, n equals 2, n equals 3. These numbers are called the principal quantum numbers. They describe, or they enumerate, rather, the quantum energy levels, the quantized energy levels of the atom. With electrons, quantum mean you could count each electron. There's 1 electron, there's 2 electrons, there's 3 electrons. With energy levels, it means something different. It means that there is a definite space between the first and the second energy level, and there's no energy level in between. The electron goes from one to the other without passing in between. You can't have an electron in hydrogen that has energy in between those two levels. It doesn't exist. So, anyway, hydrogen. Very simple atom, but very well described in this theory. And here is another equation that is used to this particular equation is used to actually calculate. Sorry, this is not the right equation. This equation is used to calculate those energy levels using the light coming from the spectrum of these atoms. Again, we knew before that if you multiply Planck's constant times the frequency of light, you get the energy of something. And that, Bohr surmised, would just be equal to the difference in the energy between those energy levels. Seems simple enough, but it took a genius to figure it out. Right? So it ends up just being the difference in energy levels is equal to the frequency of the light that you see as the electron jumps between those levels times the Planck constant, h. So simple enough. The problem is that once you start messing with these energy levels, if you mess with them at all, for example, if you bring in a little bit of magnetic field, if there's magnetic field involved, and there always is, magnetic fields are everywhere, then you start to see these energy levels split a little bit. Instead of having just one energy level at n equals 2, you have more than one for some reason. And this was explained by saying these electrons must have some magnetic characteristic. And eventually it was determined that it was angular momentum. That the electrons have some kind of angular momentum associated with them, and that angular momentum, I mean, it'd be kind of like the electron as it goes around and around. If we considered it to be going around and around the atom, it would have angular momentum, right? It's not really doing that, but it still behaves as if it was doing that. And so this angular momentum characteristic also turns out to be quantized. It's not just any old angular momentum. It's specific values in specific atoms. And that was determined here by this formula. This formula was determined from those observations. And again, Bohr was the one that came along and did this, and he didn't understand why it should be quantized, but it was. And you can't really argue with the evidence. You know, you can make theories about why it does it or why it doesn't do it, but you can't argue with the evidence. And so the angular momentum of an electron in an atom, in hydrogen in particular, is equal to the mass of the electron. Classically speaking, it's equal to the mass times the velocity times the radius. However, in the atom, it's equal to n, where n is the principal quantum number, 1, 2, 3, 4, so on and so forth, times Planck's constant divided by 2 pi. That's what it ended up being. And there's a way to get from the classical to the quantum in kind of a voodoo way, but really it just came down to what's it actually doing. And so you have this quantized thing. It can be 1 times h over 2 pi, or 2 times h over 2 pi, or 3 times h over 2 pi, but it can't be 2.5 times h over 2 pi. It can't be. It is these specific values that they measure. And so that is an additional type of energy that the electrons have in the atom. It's an addition to the energy of being in particular levels, principal quantum levels. Now, as we started to calculate these things, the energy levels, the angular momentum, they said, well, if we have these things, if you have the energy, the amount of energy that's in there, angular momentum that's in there, you should be able to use that to calculate the radius of the orbit of the electron. Even though it's not orbiting, you should be able to calculate the average distance that the electron is kicking around the atom. And they did calculate this. They ended up calling it the Bohr radius, and it's usually shown as a sub b, the Bohr radius, and it ends up being h squared over 4 pi squared divided by the mass of the electron divided by k, which is the Coulomb's constant, and divided by q, the charge of the electron squared. It ends up being 0.529 times 10 to the minus 10 meters, which is the size of the atom, essentially. This is the radius of a typical hydrogen atom in its ground state. It's about what we call half an angstrom, and you get to about an angstrom if you consider the diameter. So 10 to the minus 10 is an angstrom. It's 1/10 of a nanometer. So 1/10 of a nanometer is the size of a typical atom. And it turns out that the hydrogen atom is about the same size as all of these atoms. Even the really big ones, the really massive ones, are not much bigger than that. Maybe you might have some atoms that are 5 times as big or 10 times as big, but not terribly big. So, energy, energy, energy. As you go through all this stuff and you start to make comparisons with classical stuff and the stuff they observed, they were eventually able to calculate the actual base, or the lowest energy state, as we call it, which would essentially, what this tells you is how much energy is required to remove the electron from an atom. They were not only able to do this experimentally, just by trying to do it and seeing what that number is, but they were also able to theorize it. And it turns out that for hydrogen-like atoms, for atoms that have a nucleus with however many protons and only one electron, that means it's hydrogen-like. If atoms are like that, then the ground state energy is going to be 2 times pi squared times the charge of the electron to the 4th power times the mass of the electron times Coulomb's constant squared divided by h bar squared, or divided by h squared, which is 13.6 electron volts. And that is true if you have z equals 1, which is 1 proton. If you have z equals 2, you have to multiply 2 by 2 squared and put that in there. So this is with 1 squared. For helium, it would be 2 squared times 13.6, which would be 4 times 13.6. So it would have a much deeper ground state. This is what we call the ground state of the atom. It's what is required to remove the final electron from any particular thing. For hydrogen, you need 13.6 electron volts to remove an electron from that deepest state, or that closest state that an electron can have to its nucleus, to the hydrogen nucleus. And you can actually calculate the energy levels for different states above that state as well, by dividing by n squared. For the second state above the first state above the ground state, which is n equals 2 state, then it's less. You take 13.6 and you divide by n squared. And they always have a negative on it, because these energies are considered to be negative. These are potential energies. We can think of them as the energy is stored in a bond. It's stored in the bond between the electron and nucleus. So it's always a negative energy, or a potential energy. Here's another demonstration, or another illustration of how those spectral lines are formed when you observe the color coming from a lamp. Remember that the Lyman series are series that are created when an electron jumps from a higher state down to the first state, down to the ground state. So here's the Lyman series. There are all these really long lines. That means they're really high energy, which means they're short wavelength, or high frequency. The Balmer series, which is the one we can see, is all falling down to the second state. So they fall from these upper states down to the second state. You get the Balmer series. The Passion series are all up here. Those are even lower energies there in the infrared. They fall down to the third state, and so on and so forth. And these go on ad nauseum. These states up here are hard to see because the difference between them is so small that the energy coming out is really, really small. So the wavelengths are really, really long, radio waves and things like that. So they're harder to see. If you give the electron all the energy it needs, 13.6 electron volts, it will jump from this state all the way out of the atom and overcome all those energy levels. And so here are all the equations for Bohr's theory. Okay, let's see how many sections we have here. X-rays. Yeah, let's do a couple more sections here. So, remember the atomic spectrum. The atomic spectrum of each atom is different. We normally only talk about the ones we can see. This is a visible spectrum from iron, it looks like. So this is from iron. You can see it has a lot of different lines and a lot of different energy levels. Because iron, if we look down here on our table, where is iron? Iron is, I can never remember which numbers they are, so I just have to look for the code. There it is. Iron is 26. 26 protons, 26 electrons. It has a lot of interactions going on. And the more you have, the more electrons you have, the more crazy this spectrum gets because of all the interactions that can happen. It creates all these crazy energy levels, right? So the spectrum of iron is really crazy. The spectrum for hydrogen is not nearly so crazy. You're just going to get a few lines in the Balmer series, and they actually show them right here. The lines that you can see in the Balmer series that are bright are 1, 2, 3, 4, 5. There's only 5 of them that you're really going to see. And so that's the hydrogen spectrum would be much less. I mean, there'd only be 5 colors. There'd only be 5 lines here for the hydrogen series, for the hydrogen spectrum. However, you can see that they have these big jumps, the big jumps that go down to n equals 1. These big jumps are electrons that have a lot of energy. And any electron that you pop out of this n equals 1 state is going to have a big energy itself. It's going to release, you're going to get some kind of big energy. Either an electron coming out will be given that energy to come out, or if it jumps up to one of these higher states and then falls down again, it's going to release high energy light. And that high energy light could very well be an X-ray. Because it has such high energy, it has a very short wavelength, it becomes an X-ray. And that gives rise to this idea. As you have X-rays being emitted from a particular substance, they get these spikes in them that are characteristic, that are specific to a particular type of material. Every material has its own spikes, which they call characteristic X-rays. And how do you make X-rays? Well, we talked about this before, I think. Maybe we didn't, I can't remember. Did we talk about how X-rays are made? What's that? So X-rays are usually made by bombarding a piece of material with high energy electrons or high energy particles of some kind, and letting those particles be slowed down by the material. And as that material slows down those particles, one of the things that happens is those high energy particles, those high energy electrons, might knock out an electron low down in the structure of an atom. And if it does that, it will create this spike at that particular energy level. And since we know the energy levels of atoms now, we can figure out what kind of material is slowing down those electrons. So every material has its own characteristic X-ray spectrum like this. This kind of hump underneath it are all the X-rays that are created just by not knocking out an electron. You could think of it as electromagnetic friction as these electrons get slowed down within the material. They call it breaking radiation, or Bremsstrahlung in German. But anyway, as you create these X-rays by slowing down these high energy particle or high energy electrons, you do get these characteristic X-ray peaks out in this broadband X-ray radiation here. The great thing about X-rays is that there's such high energy as they go right through things. They have such a short wavelength that they can travel between even densely packed particles in many cases. So you have to have a really dense material to stop them, a dense material like a metal. Particularly lead is good at stopping X-rays. So how do we calculate these X-rays? We're going to calculate these X-rays using the same essentially equation that we've used before for the energies in an atom. That's this equation right here. The energy of an energy level is equal to z squared, which is the number of protons, over n squared, which is the energy level that we're looking at. So if we go from E1 to E2, that's going to be a big jump, so we can calculate that energy. E1 to E2 is going to be z squared over 1 squared, because it's going to be the n for this is going to be 1. We calculate that for this particular one, which is z is 73, they say. They've given us the z for tungsten, effective z, 73. You square the 73 divided by 1, multiply by 13.6, and that's the energy of the ground state, n equals 1. To get the energy of the second state, you do that same thing divided by 2 squared, so it's all these numbers divided by 4 instead, and you get negative 18.1. So this is the deepest state, or the lowest state, or the ground state. This is the next highest state. We need to know the difference as an electron jumps between these two states. As it jumps from 18 down to 72.5, you're going to get an energy difference, and that energy difference is going to be released in the form of an X-ray. That X-ray is going to have 54.4 kiloelectron volts of energy, which happens to be an X-ray. It's a soft X-ray, not a terribly strong X-ray, but it is an X-ray. Most of the time, if we're going to look through bone and see bones and things like that in your body, you're going to need an X-ray about in the 100 electron volt range or 200 electron volt range. But this one, it would be a good one for mammograms, for example. Soft tissue X-rays. So they show some examples of how X-rays are used. One thing that they don't show is they don't show the CAT scan. Here they're showing a CAT scan. So the CAT scan is an X-ray machine that has a rotating X-ray emitter and a rotating X-ray detector. So there's an X-ray emitter on one side, an X-ray detector on the other, and usually there are multiple ones. And this thing rotates around your body, rotates around your head, and takes X-rays from many different angles and also many different energies. Sometimes there'll be lower energy, soft X-rays that'll go through the soft tissue and not through bones. Sometimes there'll be high energy X-rays that do go through the bone. Depends on what they're trying to see, what they're trying to detect. They'll use different things. And then sometimes it just goes around once. Sometimes it goes around more than once to get a higher resolution. But as it does this, it creates these different, what they call slices. So it shows an image from this direction, which is a slice, and then from this direction, which is a slice, this direction, which is a slice. And then they use a computer to put all those slices together to create a three-dimensional image. And you can get something like a three-dimensional image of the skull or a three-dimensional image of the brain. And you can see things with more detail. And because they're taking many images from many angles, they can get higher resolution. And they use a computer to do that. The most important thing about a CAT scan is the computer modeling. The computer takes all these images and creates a model of the thing that they're trying to image. So that's what CAT scan stands for. CT scan is computed tomography, CT. And that's why they call it the CAT scan. CAT scans are pretty dangerous for a human because you get a lot of X-rays in your body, and X-rays are high energy and can start to break down your DNA. And when your body has broken DNA in it and tries to fix it, it often makes mistakes, and those mistakes can turn into cancer. That's why X-rays are bad for the body. Lots of X-rays. If you just get a few X-rays, the chance of it turning into cancer is pretty low. But the more X-rays you get, the more your body has to fix, the more mistakes it's likely to make, and the more higher chance you have of it becoming cancers. Rosalind Franklin. So, did anybody know who Rosalind Franklin was? You might recognize, you probably wouldn't recognize this particular picture. This is one of the pictures that she took, but this is another one. Let's see if I've got one. I'll find another one. I thought I had one up on that poster, but I don't think I do. You'd probably recognize the two people she worked with, but I won't give you their names. So Rosalind Franklin, this is the picture that she took. Right here. Recognize that one at all? This is an X-ray diffraction of a crystal of a molecule. One of the bigger molecules in life. And it's a molecule that forms a double helix, DNA. Rosalind Franklin was the scientist who took these pictures using X-rays. So what she did is she had these crystallized DNA molecules, and she shot X-rays at them. And as the X-rays went in and encountered these crystals, they diffracted and interfered with each other. And they created this interference pattern, this X-shaped interference pattern, which is the kind of interference pattern you get from a helix, a double helix, a ladder that's been twisted. And she was able to determine that DNA was a double helix from these experiments. And then they started to understand that the rungs of the ladders were made of these different amino acids, that there were certain amino acids whose combinations would fit together, others that wouldn't. And they started to understand the structure of DNA and the function of DNA from there. And then really, that's the building blocks of life, right? And Rosalind Franklin was the first person to do this. Have you ever heard of other scientists associated with this? For example, the ones that got the Nobel Prize for this? Two guys named Watson and Crick. You ever heard of them? Watson and Crick? Watson and Crick got the Nobel Prize for doing this research because they were doing it at the same time and worked with her. However, she died before the Nobel Prize was awarded for this. And so she wasn't allowed, you're not allowed to receive the Nobel Prize posthumous. I'm trying to find Watson and Crick right here. Some people say that they stole her idea. I don't think they really stole her idea. Some people like to say that to inflame sexism things, but they got the credit for it because she just died before the Nobel Prize was given. But anyway, that's Watson and Crick right there. There certainly has been sexism in science. There's no doubt about that, but I don't think that was necessarily the case in this particular example. The Nobel Prize Committee gave the Nobel Prize to Madame Curie, Marie Curie, long before Rosalind Franklin did her experiments with DNA. So it's not like they were sexist on the Nobel Prize Committee. They recognized women early on. She got the Nobel Prize in 1906, maybe, pretty early. One of the first Nobel Prizes. I think maybe she may have gotten the first Nobel Prize in physics, actually. I can't remember. But anyway, it was certainly early on. So that's what we call this crystallography, and it's something that is done a lot today still. In fact, one of the uses of crystallography is used to determine the form that crystals take in materials, rocks and metals and things like this. And on the second Mars rover, I actually worked on this project where we were designing a X-ray diffraction spectrometer, where we used an X-ray source that I designed. This tube did I show you guys this X-ray tube? So they used this X-ray tube, and this X-ray tube could create not only the spectrum of X-rays so that you could figure out what a rock was made of. So you could say, oh, this one's got iron, and it's got potassium, and it's got whatever in it. You could tell what was in it, but you could also tell how much of everything was in it from the heights of those lines, from the relative strengths of those signals. But you could also tell the crystalline structure from it, because at the same time it was taking this X-ray spectrometer, it was doing this X-ray spectroscopy, it was also doing X-ray diffraction. And so it was determining the crystalline structure and how this rock was formed, what kind of, if it was an igneous rock, if it was some other kind of sedimentary rock. You can figure that out, and so you can figure out the kind of geological history of Mars with the second Mars rover. And it was a very cool experiment. It involved a lot of computer like a lot of computer work. It required three-dimensional computer tomography, essentially, which was very difficult to do. In fact, the engineers at the company at the time, the engineers and physicists combined, couldn't figure it out. And I was in a meeting with all these scientists one day, and we were trying to decide what to do about this. And I raised my hand and I said, I know somebody who can do this. At the time, I was the teaching assistant for quantum mechanics class, and in that quantum mechanics class, there was this kid who had not missed a single problem in his homework or exams the whole semester. He was so brilliant, so smart, and reminded me, and the character in The Big Bang Theory, Sheldon, reminds me of him a lot. They both had very interesting social challenges, and their minds just worked in a very different way. And this particular kid was also extremely good at programming computers, doing computer programs. And I'd heard that, but I didn't know it firsthand, but I heard it. And I said, we should give this kid a try. And so we brought him in, and this kid comes in, and I warned him beforehand. I said, he's a bit strange. He always looks at the floor. He'll almost never make eye contact with you. And he has a tic. He has a nervous tic all the time where it blinks and he fidgets with his head. His head does this weird jerk and he blinks really hard while he talks. I said, it's nothing to worry about. It's just his peculiarities. But he is really brilliant. They'd been working on this for 6 months, and the guys they had working on it were brilliant. One of them was a kid who had terrible grades in college. His grades in college were like barely C+ kind of range. It was just he never did anything in class, never did anything at all in class, but he was brilliant in the laboratories, and he still got into a top 5 university. He went to the University of Maryland, he went to the University of Wisconsin, which is a top 5 university in particle physics, and went off to Switzerland, I think, to do research at the Large Hadron Collider. Just a brilliant scientist and brilliant with computers. He couldn't figure it out for 6 months. He and his team of engineers were trying to work it out, and they couldn't figure it out. It was just screwed up. And this kid came in. He had never programmed in the language they were using. He'd programmed another language, but he had to first learn the syntax and the language that they were using. He had never programmed on the type of computer they were using. And in 6 weeks, he had figured it out, and he had cut the program down to make it simpler so it would run faster. And he had done everything to make it work. I mean, he earned a PhD in 6 weeks if he had only been a graduate student. He would have earned a PhD just by that one single project. It was just brilliant. He just came and did it. Sure, why not? I have no idea. Something brilliant, I'm sure, but I have no idea. He could have gone to any school he wanted to in the entire world as a graduate student. He went to BYU because his father was a professor there. His father was also quite smart, but not brilliant like his son, I don't think. But certainly not brilliant like his son. But BYU is also a very highly regarded undergraduate physics program. So a lot of students from there go to places like Princeton, Oxford, and other places. So he could have gone anywhere. I don't know where he ended up. I don't remember. I don't think it had a name. It just had a designation. It was NASA program number something or other. I don't know. It wasn't any particular program. But it's up on Mars now. So.
If you had X-rays shot in one particular part of your body, would that end up being constantly?
Yeah, and that happens a lot. In fact, they use X-rays to obliterate cancer cells. So they'll concentrate X-rays, and they call it a gamma knife, actually. They're not really X-rays. They're higher energy than X-rays.
If X-rays cause
Yeah, X-rays can cause damage that can cause cancer, but if you do enough X-rays in one place, you can actually just completely, well, and usually you have to go a little higher energy than X-ray. You have to go to the gamma ray spectrum, which are the same thing as X-rays. They're just lower They're small, they're shorter wavelength and higher energy. But eventually you can use those to just completely dismantle the molecules in your body. And that's what they do with the gamma knife. The gamma knife is this device that is usually used for things in the head, because if you have a tumor in your brain, it's cutting open the brain will turn you into a vegetable. It'll just kill you. You just can't cut into the brain very much. So you, instead of cutting into the brain, you use the gamma knife. And let's see if I can make this bigger. Here we go. Well, that's nice. That's not very big. So what they do is they surround your brain, surround your mind, your head with all these different gamma ray sources or X-ray sources, and so that they all overlap at a single point in your brain. And where they all overlap, you get a concentrated gamma burst right there that will just take apart the molecules. It'll completely dismantle every molecule. That includes cancer. Everything in the cancer cell will just be taken apart, and you'll just have atoms left, or small molecules, small like amino acids. And your body just recycles those. And so that's usually what they call radiation therapy for cancer patients. They use the gamma knife and other similar instruments to. They also have one called a positron emission topography, I think they call it. But it's the PET. And that one uses high energy positrons, which are like electrons, they're the antimatter particles or electrons. And those they bombard your skin with to get rid of cancer cells on the surface of your skin. Because those won't go very deep into your body before they lose their energy, but they will kill the cancer cells in your skin. So, and they use other ones for other things. They actually have little radioactive seeds, little radioactive bits of metal that they can put inside of a tumor. So if you have a tumor like in your body somewhere, they can put a little radioactive seed inside of that will kill the tumor. And by the time it's killed the tumor, it's not radioactive anymore. So they have all kinds of methods for delivering radiation to the body to kill things off in your body. Lots of different methods. We'll learn more about those as we get into the next chapter, the radiation chapter. But yeah, the gamma knife is certainly an interesting way of using that stuff. Why is it that this section is not coming up?
Supposedly, Jesse from last semester,
Yeah.
he showed me a video about NASA trying to create a type of engine that, we were talking about Interstellar and how
An engine that could get
the
you.
speed of light.
Yeah.
We're trying to create an engine that kind of makes like a warp time to do that.
Well, that is a fictitious engine designed by Star Trek story writers. They're not making one that does that now. They're not even thinking about it. First, we have to understand what that means. We're still learning that, but we're learning quickly. That's the experiment that was done last year detected the first ever warp in time. That was the first gravity wave is what we call it. A warp in time. Warping time is actually a misnomer. Time in physics literally doesn't exist. There's no such thing as time when you start talking about physics in these ways. In fact, in reality, there's no such thing as time anyway. But time is something man made up. But if you're starting to think about this, you have to think about what is space. And it turns out that space is something that is not constant. It's not flat, it's not straight, it's not even constant. It changes. It's bending, it's warping, as we call it. And the first time we ever detected a warp in what we call space was last year with the LIGO experiment. And that's something that Einstein predicted would be possible. Well, his theories predicted would be possible. It was somebody else that predicted it later. But it was only just last year that we actually were able to detect it. So that's really kind of exciting. Once we start understanding that a little bit more, then maybe we can think about, actually doing that. But we're talking at least hundreds of years away for that. in my opinion. That's something, I mean, it's exciting that we're at that point now, because we never imagined we'd be where we are today, even observing it, being able to detect it. But actually being able to manipulate it using something that we understand, we have no way of, we don't even know what would manipulate it at this point. The only thing that we know that manipulates it is huge, massive things like black holes. So if we could, manipulate a black hole somehow, that's the only way that we know that we can do it. In Star Trek, they use these fictitious materials that interact to make this matter-antimatter thing, to create this event. But, that's all fictitious. There's no way to, that's not what we would do as far as we know. We would have to learn some more and figure out something else. So that kind of engine is not in the works by any means at this point. Yeah, it's not neither theoretical nor practical in development. The idea is all fictitious, but we are learning now about warped space, since we're starting to measure it. So we have a lot of theories about warped space, but we don't have any kind of practical theories or designs for engines in that way. We do, however, have ideas for other types of engines. Plasma-based engines, nuclear-based engines, radiation-based engines that could get us going pretty fast. But some kind of engine that would actually manipulate space to get us going somewhere, because that involves so much more. Remember when we were doing relativity, we learned that the momentum of something that is moving close to the speed of light increases, which is, you can imagine it being kind of like the mass increasing. But if your momentum increases infinitely as you get closer to the speed of light, it requires an infinite amount of force to continue your speed. So you have to do something to change that increasing momentum, because there's no such thing as infinite force, right? Doesn't matter what you do. So you have to do something to not only would you have to warp space and time, but you have to warp momentum and energy. It's things that we have no grasp on yet. We have just no idea what to do. So, and no measurements. There's no appreciable measurements of those kinds of things either. So, we'll go ahead and finish up there today. We'll start on the excitations and de-excitations applications next time. Tomorrow we will do some experiments involving atomic physics. We'll take a look at some spectra of atoms and in gas forms. We will also hopefully do some other things, some fun stuff. Here they talk about lasers and how they're made, so that should be fun too. But anyway, we'll see you guys tomorrow.